much. Okay. All right. I'd like to welcome you back to the second part of this talk on Morpheus. We're going to be discussing here how we can integrate algorithms and build on top of the sort of data shaping that's taken place in the first part of the talk that you've seen in Martin's demos and examples. We'll also be talking about the Spark project improvement proposal, a little bit of detail on that, and also what's going on in the related world of standards for graph querying, because there's a lot of impetus in the industry more broadly, extending beyond Neo4j, beyond the Spark environment, to actually mature a standard for graph querying, which would take Cypher as one of its inputs. So super quickly, because a lot of people I think were in the first talk, we can create graphs from data sources, we can wrangle graphs in terms of projecting new ones, combining graphs, dividing graphs, and so forth. We've seen examples of that. We can go tables to graphs and graphs to tables. We can analyze graphs, and we're going to see a lot more about that in this part of the presentation. And we can also create a library of cataloged graphs by storing graphs into the file system and also pushing data back as labeled subgraphs into Neo4j. What we now want to discuss is how that sort of intersects with the world of data science. You can take this bit?
No, that's your part.
That's my bit. Oh, he's going to give me this bit. Okay, I'm going to do this bit. So we went back and forth about what the division of labor would be here. So we're first of all going to concentrate on the combination of Neo4j and Spark and the use of graph algorithms and the interchange of data with Neo4j or between Neo4j and Spark, and we will also discuss the Spark project improvement proposal, which goes under the overall component name of Spark Graph. So we've got, and if people might have attended Amy and Søren's talk earlier on this morning, which went into a lot more detail on this. I'm sure that the recordings will be available and the slides will be available. There's also a new book that's come out, co-authored by Amy Hodler and Mark Needham from Neo4j on graph algorithms, which explains how to use graph algorithms both with Spark and in Neo4j. But overall, that's part of a picture for Neo4j, an emerging picture of graph analytics. So Neo4j is a database that has historically been focused on operational transactional capability. We've got that database. It's a very mature database at this point. We're heading towards a version 4.0 as the next version of the database. And we've got the Cypher query language. These are familiar things. We've also got a wide range of procedures that let you use a more detailed API to carry out activities that you can't carry out using Cypher, and you can write your own procedures as well. We've got these native graph algorithms, native because they exploit the characteristics of the Neo4j database. They actually introduce a new native format that's optimized for graph algorithm processing, and we're trying to exploit the speed that you can get from having an in-process, single host, single memory image processing of graph algorithms, which is something that obviously would not be available within the Spark environment. And in many contexts, if your graph is small enough and you can fit it into memory, or if you've projected out the right kind of subgraph, that can be the fastest way of actually working with algorithms. And we're also working on how do we integrate with other analytics capabilities. So one example of that is the work that we've described here with Spark. And we're interested, I think, in a longer term about how we can provide ways for Neo4j users to exploit graph analytical capabilities and non-graph based analytical capabilities in a unified offering. So this is really the beginning of a road. And Jake Graham, who's I think at the back of the hall, is the product manager who's responsible for this picture. I'm sure he'd be happy to answer more detailed questions about how that might develop. What we're seeing to begin with is early adopter program releases and experimentation with both graph algorithms and some of the features that you've seen with Morpheus. And there's a picture that will develop over time of a roadmap of commercialization around the current open source offerings that we've been describing. So the Neo4j graph algorithm library is listed here. I won't go through everything that you can see, just to point out if it's got an asterisk and it's in italics, it's also present within GraphFrames. So it is a superset of the algorithms that are available within GraphFrames, or going back to the GraphX origins. You can read all about it. You can read the book. There's tons of stuff going on at the moment. A very exciting development to be able to actually bring graph data and graph computation together in this way. And we're interested, incidentally, on the query language side about the more general issue of not just algorithms as such and well-defined functions, but how could you integrate graph computation with querying of data and so forth. So there's a lot to think about in a sort of a developing next generation of this kind of technology. There's the book, the very one. So I think you can easily download it. It seems to be moving off the virtual shelf very fast from what I can hear. Okay. Is this your yes. bit now? Have I got it right? Okay. All right, I'm going to pass back to Martin to talk about some of the more concrete possibilities and cases and how it actually integrates at a code level.
Thank you. So in this part of the demo, we want to now show how the graph projections that we created in the first part of the demo, or in part 2 to be precise, are used to run graph algorithms on top and to find some analytical value within the data. So we want to use the PageRank algorithm, which I guess most of you know. It's basically an algorithm that you use if you want to measure influence in a network. It became popular through Google and its web search engine. And it's also used, for example, to run personalized PageRank in Twitter to do recommendations for users. And you can also think about using it in fraud detection. So what we want to do in this part 4 is we take two input graphs, our graph projection that we built earlier, the business co-reviewed business projections on the left-hand side, which means two businesses are connected if they have been reviewed by the same user. We want to run PageRank on both of those snapshots from 2017 and 2018. We want to bring those graphs back together, and then we compute something we call trend rank, which is basically the difference between the PageRank of 2018 and the PageRank in 2017 to find out which businesses have an increasing popularity. So in order to do this, we have part 4, which is, again, all available online. You can just look it up on GitHub. I have Neo4j Desktop running. This is an app you can download, which allows you to manage multiple Neo4j databases. You can run graph algorithms in Neo4j. You get the browser to visually explore your graph. And I have one database running here, which is currently empty. And I will just run this demo and explain while it's running. So as you saw from the first parts, we always have to initialize a Morpheus session, which we do here. Then we have two data sources that we need now. We have the file-based data source, which we use to load the snapshots from the local file system, but this could, of course, also be HDFS or S3. And we have a second data source, which is the Neo4j data source that we initialized using graphsources.cypher.neo4j with a Neo4j config, which is basically including the bold URL that allows you to connect to Neo4j and some authentication information. So then for the 2 years, 2017 and 2018, we basically copy the snapshot, the business co-reviewed business snapshot graph from the file system into Neo4j, which means from the file system we create a new graph in the Neo4j namespace, which is the namespace we use to register the Neo4j graph data source in. And we have a specific name, which is co-reviewed and the year. And then as soon as we store this graph in Neo4j, we run a Cypher query directly in Neo4j that is we use the Neo4j config here. And this is basically the call which runs PageRank inside Neo4j. It's called call algo.pagerank. You can limit the algorithm to just run on a subset of nodes that are identified by a given label. You can also specify a Cypher query that selects those nodes that you can run the algorithm on. Here we just use the meta label that we use to identify nodes that belong to a specific graph within Neo4j. Because as you know, Neo4j does not support multiple graphs, but we use the label to distinguish nodes that belong to different graphs. Then we have some parameters for the algorithm itself, like how many iterations are being run, both directions, incoming and outgoing relationships are being used. And the output, so the page rank for each node should be written as a new property, which is page rank year, so 2017, 2018. And we want to use the review count that we stored on the snapshot, which is the number of users that's reviewed those two business, as a weight property for the algorithm. The output is then the number of nodes that have been affected and how long it took to run, which you can see up here. So we did it, those graphs are pretty small. It just takes 57 milliseconds in Neo4j to run this. And then we bring the graph back, which you can see here. So now we are on Spark again. So this is a Cypher 10 query that you run in Morpheus. What we do here is we create a new graph called business trends graph, which should contain the businesses and their trend rank. And it's basically the input from those two graphs. The first one is the 2017 graph. We get all the businesses. The second graph we want to use is the 2018 graph. We return all the businesses, and we join them back together because we want to bring those graphs together. And then on the join graph, we can basically return the business, and we compute the trend rank, which is basically the normalized page rank of 2018 minus the normalized page rank for 2017, and store this as a new property at the business, which we call trend rank. And the output is a new graph that contains just the businesses with this additional property. And then we can use this graph to match the businesses, order them by trend rank, and show the top 10 here, which brings us to the output that you can see here. And here we see a normalized page rank between 0 and 1, which descending sorted shows which businesses in Boulder City have an increasing page rank between 2017 and 2018. The second example we want to show is using two algorithms. The first one is Louvain modularity, which is a community detection algorithm that allows you to detect connected nodes or kind of nodes that belong together in a community within a large network. And it's also being used for money laundering, so also fraud protection and fraud detection, sorry. And you can use it, for example, in protein-protein interaction networks. And the second algorithm we use here is not a graph algorithm, it's a set similarity algorithm called Shakar similarity, which is basically the intersect divided by the union of two sets. And we want to use Shakar similarity to find similar users. So the use case here is we take the third projection that we built in our graph snapshot library that contains the co-reuse relationship between two users. So two users are connected if they review the same business. And it also contains the original reviews relationships to the business. So at first, we want to run the Louvain algorithm to detect communities within the user co-reuse business subgraph. And then for each of those communities, we want to find similar users within the community, which means two users are similar if they reviewed the same businesses. And then we want to recommend businesses to users that they have not reviewed before, but similar users have. That's the idea. And in the code, just run this again. It's again very similar. So we need two property graph data sources, one to load the graph from the file system, our snapshot that we are using, Neo4j data source again. We copy over the graph to Neo4j. And then within Neo4j, we run at first Louvain to detect the communities. It's very similar to the PageRank call, except that it's taken different arguments, of course. We also want to store the resulting community ID as a new property, which is the right property option. We just call it community year. So this is basically the community ID that that identifies the community the node belongs to. And we just use the co-reviews relationships, so not the reviews relationships. So it's just the relationship between the users. And then this algorithm basically outputs the number of communities it has been found, which is very useful for our next step, because we want to take this number of communities, and then for each of those communities, we want to run Shakar similarity within the community, which requires us to at first select all the businesses a user has reviewed. So we are looking for this pattern. And then we basically say the input is the user ID and the IDs of the businesses it has reviewed, which is taken as input for the set similarity between users. And then we can run the Shakar algorithm. So the cutoff means that if they are 50% similar, so if there's a 50% overlap within the two sets, they are defined to be similar, and we create a new relationship between those two users. which is called is similar 2017 in that example. So after that, we are back in Spark, and we can run a Cypher 10 query, where we basically read the graph again from Neo4j, which has the new relationships. So we're looking for users that are similar to each other, which is the first part of the pattern. We want to find out which reviews one of the users has reviewed, and we want to find out the businesses the other user has not reviewed, and the review that the first user gave has to have more than 3 stars. Which brings us to all the businesses that we want to recommend, and the output is then the username of the second user and all the recommended businesses this user should have a look at, which you can see in the output. This brings us to you.
Okay, so just a quick description of what's going on with the Spark project improvement proposal that we've mentioned. So at the core of this, we want to create a property graph type, which is based on DataFrames. And in addition to that property graph model, we're also looking at the Cypher query language and moving GraphFrames algorithms over to be implemented over that property graph type. And the plan is at the moment that this will come in Spark 3.0. Obviously, that depends on how things evolve and all the other competing claims and so forth. But the proposal was accepted by the community and is being actively worked on at this point by technical staff who are involved in Neo4j and Databricks. The idea is that the motif-based querying that you see in GraphFrames, which is a very simple edition of the kind of pattern matching that you can do in Cypher, and which doesn't then carry out some of the sort of post-processing and some of the complexities, that things like variable length, multi-hop queries, pattern matches, and so forth that you can do in Cypher. That will be replaced by the fuller functionality of the Cypher language. Particularly because Cypher's, has played a significant role in creating a kind of de facto standard around these multiple implementations and has got a very wide user base. So there's a lot of people familiar with Cypher. We're also, the plan is that the GraphFrames algorithms will be re-implemented on the property graph type as part of this work. The way that this is going to happen is everything, what we've shown here in Morpheus, a very wide area of functionality, including, as Martin was just demonstrating, this ability to take graphs, subset them, split them, combine them, incorporate new information on top of an existing graph. It's a very, very sophisticated, composable query capability. But at the heart of it, and at the beginning of it, was what we call Cypher 9, which we mentioned earlier on. That's to say, the kind of Cypher that you would be familiar with if you use the Neo4j product, for example, or another company's product that implements Cypher. So an example recently, a company called Cambridge Semantics has implemented Open Cypher. It's the kind of capability you'd see with those implementations. And that is, the limitation with Cypher 9 is that you do the pattern match and you get back a tabular result, which is very useful, and we've seen examples of that in what Martin's been talk about. So I think the thinking was that we shouldn't try to bring too much at once into the Spark core project, that we should try and take incremental steps and move over the boundary towards a property graph-based model and begin the process of providing this kind of more sophisticated querying capability. And having said that, the actual technical design that's been proposed for the SPIP is very much modeled on what's been done within Morpheus. So this is like taking a subset of Morpheus and bringing it into the core Spark project. And I think a question was asked relating to this. Everything in Morpheus at the moment is purely a Scala API, and we want to move beyond that and have to move beyond that for the core Spark project in terms of Python and Java. So the things that aren't happening in the SPIP is any kind of modification on the existing property graph data model. We are trying to address the property graph data model. We're not trying to address wider or different models like the RDF model and so forth. We're not dealing with the Cypher 10 multiple graph, composable query, and view capabilities. And we're not at this point trying to introduce a catalog entries in the Spark catalog for property graphs or the property graph data sources that we've heard described. And here's the link. There's an example of how this might look from, so there's bit work gone on to have an API which could, which is based around the concepts you've heard in terms of taking DataFrames tables for nodes and relationships. The builder pattern that Martin used in some of his examples could be overlaid over this core API, so probably wouldn't have to look very much different at all, but this would be the sort of raw API. And therefore, in the core project, the building of a graph would not happen with the assistance of these more sophisticated property graph data sources. It would be a matter of creating and having the appropriate data frames and then composing those to actually create the graph. Interesting point coming off that, how will Morpheus and that core project relate to each other? How do we avoid there being a kind of, you jump off the edge of a cliff if you want to go from the core project to Morpheus? Martin's been doing some interesting thinking about that, which I think is still work in progress, but I think you can show us some ideas about how that might happen.
Right. So the link we just showed is basically a pull request on the Spark project that you can have a look at. So it contains a prototypical implementation of what the SPIP in Spark 3.0 could look like. And what I will show you now is basically how you can exchange the SPIP implementation with Morpheus. So the module ID that we are currently having is looking like this. So on the Spark side, we basically have two modules that we introduced. One is Spark Graph API that contains the property graph API, a Cypher session. And we have Spark Cypher, which is an implementation of this API, and it's a query engine, basically. And then on the right-hand side, we have Morpheus. The shared module in the middle, you didn't hear about that until now. It's called Okapi, which is basically, if you recall the different layers in the first part of the presentation, the intermediate language, the logical planning, and the relational planning, this is all happening in Okapi, which is a very generic layer. So Morpheus and Spark Cypher both implement this API, or this Okapi stack. And how the binary switch will then look like, I will just show you now. So what you see here is very, very experimental work. So what I did is basically this refers to the new module that we created in Spark. We just call it Spark Cypher. And there we have the Spark Cypher session, which is an implementation of a Cypher session. And there is a very similar concept to the node tables and relationship tables that I explained earlier, which we call node frame and relationship frame to make it more aligned with the data frame concept. And as you can see, we just create a Spark session, as you all know, a locally running Spark session. And using this, this is implicit in the context, so we just can create a Spark Cypher session, refer to this variable, Cypher session, and then we can create data frames using Spark and wrap them into node frames. And then using the Cypher session, we create a graph of this node frame, so all very similar to the demo that I showed in the first part. And then on the graph, we can run a Cypher query. So if I execute this, we should see the result, which is just all the nodes within the graph. So like this, so it's just a data frame output which contains a property, a Boolean column that declares that this row has a labeled person and an ID. And now you can imagine you want to use the Morpheus capabilities, which is having multiple graphs, data sources, and so on. So this would be the code that you see in the bottom. So if I comment this in, this of course doesn't compile because we don't have this in the SPIP as defined. So what we do instead is we don't create a Spark Cypher session, we create the cap session that we use through all the examples, and this basically makes this thing compile, and we can just run the same application using the SPIP API plus the functionality that we just demonstrated throughout the talk in Morpheus, which is registering a property graph data source, using multiple graph syntax, creating new graphs, and printing basically the nodes of this graph, which brings us to those two outputs here. So this is pretty neat, and this is how you can imagine this will look like with Spark 3.0.
Okay, so The last thing we wanted to talk about is to situate what we've been discussing here in the kind of wider perspective of work that's going on in the industry involving a number of vendors to sort of recognize the way in which graph data management has been maturing, about the significance and the increasing penetration of the property graph data model, and to say for this segment of the database industry to actually move forward, we're getting to the point where we really need some standards that don't exist so that we can make it easier for people to create tools for data modeling, ETL. We make it easier for customers to have confidence that if they move across these different environments and different vendor provisions of graph data management capability, they won't be locked in, and to make it easier to develop a single skill set for developers, which is more broadly marketable. In other words, all the advantages that come from standardization and which have been, for all the many dialects, warts, criticisms and so forth, SQL for the relational database world has been an enormously powerful and enormously successful standard in allowing a huge range of different technologies and stabs on the data management issue to be attempted and to be brought together. So we're really looking to try and actually achieve that in general, and obviously in the longer run, I guess our sort of vision would be that if you were in the Spark environment, you would be able to use SQL on the relational side, the tabular side, and you'd be able to use a parallel to SQL, GQL, a standard graph query language. So it's a bit of a fussy diagram because there's a lot of stuff going on, but at the core of this is a proposal that I originally put forward with backing from other colleagues within Neo4j back about a year ago, to say, let's get to a single standard graph query language, GQL. Let's build on prior efforts like Neo4j Cypher that then became Open Cypher that got implemented by multiple people, research work that we and other vendors and academics that were involved in to produce a paper called GCore, which was a definition of a research language which showed, for example, regular path queries and composable queries, some of which we've already seen today, emerging in industrial practice. There's a language from Oracle related to their PGX product called PGQL, which is kind of in the same family, did some interesting new things that weren't done in Cypher to do with more advanced pattern matching, path pattern macros, which are almost like mini views over patterns. And there's a lot of academic work in the background, particularly relating to regular path expressions and the applicability of those to this environment. And so we want to try and bring those things together, and we also want to piggyback on some work that was done jointly by a number of vendors to provide property graph querying extensions, read-only extensions to the SQL standard, so effectively enabling a graph query to be embedded inside a SQL select statement and then bring tabular results out into SQL, which you can imagine actually having some application in the Spark environment as well. So one way of looking at this is Cypher established this very strong metaphor of a pattern, and it's a very powerful way of actually expressing, first of all, an interest in data in a concise way and in a visual way, and also it's probably, as somebody in Microsoft SQL Server put it to me, it's probably the best way anybody's designed of actually expressing joins and complex joins. The amount of code you need to write is very, very limited by comparison to the amount of code that you have to write for SQL joins. That central concept is translated into a family of languages which actually share that kind of philosophy and inheritance. We can almost think of them as dialects of one language, and what we'd like to do is take those dialects and turn them into a single standard language. It's not as simple as that, because there are other languages which don't so directly come from that background. So for example, TigerGraph's product has a language called GSQL. We're interested in the standards process in understanding some of the benefits and the interesting innovations that they've actually brought to the table, particularly related to graph computation. This is a process which needs to be open to the inputs of all vendors and all prior projects. But the goal is to try and get a language which can condense and codify what's already been done and then end up being the basis for doing more and new things. So the more and new things, we can see on the left-hand side where we start from. There's some core things in SQL which we don't want to reinvent. So the idea here is that this GQL will be a partner, a peer to the SQL language, and there are some things that we do want to address that are not being addressed by languages like Cypher so far, or have been addressed by one of the other languages, but only to some extent, or have been partially addressed in Cypher, but not by the other languages. Bring it all together. And finally, if we can do some of those things, we can also start to get a more rational picture in terms of interoperation between the property graph world and other worlds like RDF, SQL. We can interoperate at a language level to do other kinds of graph programming. So we may want to use a traversal language like Gremlin, or we may want to use languages which are oriented towards writing graph algorithms. And as long as we have a shared type system and we've got a query language that can express what a graph is, common understanding and so forth, we can actually provide a more powerful environment for graph programming, not just for graph querying. So at the center of that, the thing that we think will detonate that development is GQL, is the standard graph query language. So there's an official version of what's going on here, and I'll talk about that in a second. There's also a community edition of this, because OpenCypher was successful in establishing a software-centric and a community view of how you should actually go about defining a language. We don't want to lose that, but on the other hand, we want to get the more official character of an official international standard. And so right now, there are two very active informal working groups that don't actually have any real organizational home. They don't belong in a legal entity. One working on property graph schema, the other working on analysis of existing languages. I think the property graph schema working group's got about 40 people in it, many different vendors represented, academics and so forth. Existing languages work very similar. We're already up to about 7 or 8 different languages, understanding what they currently do, how they correlate, where there's differences, what it might mean to actually bring them together. The idea behind all of this is that we would have a project, and we're hopefully going to have a vote, a couple of ballots coming up this month, coming month of May, and then through September at the international level, that will lead to what's called a new work item proposal within the ISO standards world. And there is a committee, WG3, which maintains the SQL standard. Its remit is database languages in the plural. In its 35-year history, it has only standardized one language, SQL. This is a proposal to add GQL to their repertoire, so that there would be two standard languages, official ISO international standards, one for SQL, one for property graph querying. And I guess in that sense, our hope would be that one day we're standing up here, or wherever the moral equivalent of up here is, talking about Spark SQL and Spark GQL. And that we've got these two models, we've got two languages, we've got a common core of shared data types, expressions, and other things like the catalog, which could probably be shared between those two languages. And as I was saying, we've created a focal point for a more extensive view of graph programming, because we've really got the idea of graph typing and all the things associated with that embedded within the GQL process. So that's the story. And I think we've probably got a little bit of time for a few more questions at this point. So again, if anybody does want to ask a question, if you could come up to the mic in the central aisle so that it can be picked up by the sound system. Yeah, please.
Thanks for the talk, guys. So you're saying this, there's now a way that if you don't want to work with your data in Neo4j, then you can work with it in these DataFrames in memory, right? Is there ever going to be like a GQL equivalent to Parquet files so that you can just persist it locally and not have to worry about a whole database?
Oh, you mean in terms of like trying to take, you're sort of like analogous with the sort of predicate push down, column filtering, the sort of assistance that provided to
just
SQL?
A file format.
Sorry?
Just a file format.
Right. So, yes, there's actually there are lots and lots of competing graph serialization formats, and there's a lot of interest in this sort of GQL context. There was a recent conference in Berlin, a workshop organized by W3C, where we were looking at all the different aspects of what might be involved in this kind of standardization, and also interoperation with the RDF world and so forth. And that was one of the things that came out very strongly, was the point you were raising, which is that there's a great deal of interest in import-export facilities, but those import-export facilities could also be the underlay in terms of a file format for graph storage. So we don't have a kind of optimized native file format representation of graphs. So it's a very interesting question and a very interesting area. It's not something we've worked on, but it's certainly something people have been discussing. So, and I think that could then start to play into the push-down story and so forth, because there's an equivalence between the two languages. There could be equivalent capabilities. But,
okay. Yeah. And then the second question is the AQL, like array querying language that a few databases are already running with. Is that being factored into this GQL thing, or is that on just like a separate track?
Sorry, what was the language you were
The array querying language? AQL,
I'm not familiar with that.
Okay.
So I don't think that it's something that's been on our radar. So I'd be interested. We're interested in anything that's relevant as an input, and it'd be great to understand more about that. But I'm afraid I'm not familiar with that. Yeah.
Thank you.
Sure.
So, can I ask a question about the internal representation of the node frame?
Sorry, about the
internal representation of node frame. Node frame. So data frame is already data frame has its own data representation in Apache Spark instead of the standard Java object. So how node frame keep representation in Apache Spark? Do you use a Java object, or do you introduce a new representation for specialized for Spark?
Yeah. So the node frame is basically what we showed in the first part. There we showed a node table, so it's basically metadata plus data frame. So the node frame tells us, the system, what are the labels of the nodes within this data frame. So it's kind of like metadata plus data is a node frame or relationship frame.
Basically, it's on data on top of data frame. So I'm afraid, is there any data conversion or data translation overhead between node frame and data frame? But based on your experience, it's a less overhead between node frame and data frame.
I mean, if you are asking about like utilities to convert like a data frame to a node frame, yes, we played around with this. I can show you some code if you want, but it's not like defined in the SPIP how this should look like. So this kind of utility that lets you easily transform a data frame into a node frame. We thought about column naming conventions, for example, things like that, but it's not decided yet, finally.
Yeah, I understand the ease of the programming, but I'm curious efficiency of the implementation.
Yeah.
Overhead, runtime overhead of the translation between two.
So it's basically a no-op because it's just a metadata that is attached to the data frame.
Okay, thank you very much.
Of course.
Yeah, I mean, just to add to that, you could imagine having a series of conventions about a regular data frame that would then mean you could interpret it as an element frame, a node frame, or a relationship frame. Or you could say that you'll approach that from a sort of an API perspective. And I think both of those things are in discussion. If at that level, and you can encode metadata in a regular data frame at the cost of redundancy. So there's some trade-offs there, and I don't think there's any sort of fixed view about how it must be done, right? So very reasonable questions, I think. Okay, anybody else? Just one last question, or are we done? We've got one last question. Or we've got somebody running to leave. One or the other.
If I want to add my own graph algorithm and make it accessible through Cypher, as a UDF, is that something on the roadmap?
I'm sorry.
My own graph algorithm.
Graph algorithm, yes. So that kind of you've raised two or three questions, try and deal with them very quickly, implicitly. One is UDF support. We don't actually have UDF support at the moment in the Cypher for Apache Spark implementation, right? So it is part of you can do user-defined functions in Neo4j. That would be an important thing to be able to do. It's sort of, in principle on a roadmap of expansion of capabilities. There's the issue of how graph algorithms would actually be executed and whether they could be executed either from within Cypher or within some kind of Cypher-related API, right, within Spark. And at the moment, we don't have implementation of the ability to call out to code using what's called procedure calls, which you'll have seen in the Neo4j code examples. That's also something that could be added, and you can, I think there was some playing around with more kind of slick APIs that would actually allow graph algorithms to be sort of directly executed on, you can imagine methods that represented the calls of the algorithms that could then be supplied on top of the property graph interface itself. So at the moment, you'd have to get yourself into a property graph, and then you'd have to use the mechanisms for algorithm execution in the same sort of manner as things can happen with GraphFrames. Again, that is also, I think, something that could be played with in the SPIP, and there are different approaches that could be taken. So, cool. Sure. Okay, I think we're probably done. Unless anybody's got, no, I think they're all going. So good. Thank you very much indeed for attending the talk, and please do follow up with us either directly or online. Thank you.